Good morning all. This is the PWM5 solar charge controller, which started off just as an electronics project. And in fact, here's the very first prototype of that project. And then it became a product after I started selling them on eBay and my website. And in the end, I sold about 900 of these things. But it wasn't all plain sailing. And one of the problems that I had continual trouble with, and I never really got to the bottom of it, was accuracy. And you can see that here I've got two charge controllers where I've written the set point voltage on the back. Now it's supposed to be 13.5 volts, but often it would be very low. This one is 13.38, and as such I rejected it because I set a plus or minus 0.1 of a volt tolerance limit for sellable products. So this was below the 13.4 lower limit, and this one is 13.62. This is above the upper limit, which would have been 13.6, and so these two never got sold. I do know now where this problem lies. I know what the source of this inaccuracy is, but for a long time I didn't, and at first I thought it might be here. On the circuit diagram we've got a potential divider, 82k and 20k, and that reduces the battery voltage down to something that the PIC microcontroller can read on its analog to digital converter input. The voltage on the battery could get up to almost 15 volts, and of course the microcontroller can only read up to 5 volts. Now you can see here that I've specified 1% resistors because 1% resistors are easily obtainable and they're cheap, and they should be accurate enough, but I did suspect for a while that this might be the problem. So to try and solve the problem, I bought some 0.1% resistors. Now initially I could only find these big ones. That's the 82k, you can see the grey band there. That's actually a red band. These are the 20k. Then I found some 0.1% in the smaller size, the 0.6 watt or 0.4 watt or 0.25, I can't remember which ones these are. And for a while I started building the units using these very high tolerance resistors. Now these are quite a bit more expensive. These I think are about 25p each rather than the penny each for the 1%. But I felt it was worthwhile to try and see if that was the source of the problem. But after manufacturing a number of these things and testing them, the inaccuracies continued. So it wasn't actually these resistors which were the source of the problem. Just a little bit more on these resistors. You can see that the tolerance is indicated by this purple band. Purple, it seems, is used for 0.1%. There's also this orange band here. Now on these resistors, they've actually put it on as an orange dot. And it's been many years since you used to get resistors with a dot on them. Resistors with a dot on them were back in the 1960s. But that's very interesting, isn't it? These ones have got an orange dot, which I think indicates temperature stability, I think. So if it wasn't the resistors that was giving the inaccuracy problem, deviation from unit to unit on set point voltage, what could it be? And staring at this circuit for a while, it suddenly came to me. The analog to digital conversion is a measurement of the voltage at the ADC input pin relative to VDD. So if VDD were changing, and that would be the voltage coming out of the voltage regulator, then that could give rise to this deviation of voltage set point when the unit was actually operating. And it occurred to me that actually this is the component that's causing the problem. This thing I think has a tolerance of plus or minus 1%, and variations in the accuracy of the 5 volts of the regulator is what causes this problem. Now, the regulator that I used in this product is actually marked KY5050, but I'm pretty sure it's a Texas Instruments part, so let's get the datasheet for that. And here on this datasheet here is the KY5050 device marking, which is the LP2950 50, so that's 5 volts, LPRE3. So that's the device that I'm using. Now it says here high VO, V out, I assume that is accuracy, of 1.4% at 25 degrees. But that's not very accurate, is it? 1.4%. And is that plus or minus 1.4%? And a bit further down, it says here for the 5-volt version, V out, output voltage, is 4.95 volts, typical 5, maximum 5.05. So that does look like 1% variation to the negative and also a 1% variation to the positive. So it is plus or minus 1%. Now that's not to say that the output from the regulator varies. This thing has very tight line regulation and load regulation of 0.03% and 0.04%. So whatever voltage comes out of the regulator, it stays at that. It just doesn't have very high accuracy, so you can't guarantee that it's 5 volts to start with. Now I could have used a select on test approach, so I would put each of these voltage regulators in a little test circuit, measure the voltage coming out of them, and then only use the devices that were very close to 5 volts. And I think I got the price of these down to about 18p by looking around for the best value seller. I think these eventually came from Farnell, and at 18p, rejecting half of them wouldn't have been a complete disaster. But there is actually another way of correcting this error, which wouldn't have involved any cost loss at all. And that is to write into the microcontroller on each unit individually while they were being tested a calibration value to offset the error in the voltage regulator and bring the set point of the unit back to exactly 13.5 volts. And I did come up with a way of doing it, but I never actually implemented it. And the technique would have involved this pin here, the reset pin, which is not connected and not actually used. So you can see here that pin 4, I think it is, of the microcontroller. Let's just have a quick look at that. Yeah, there's pin 1, so this is pin 4. Pin 4 is not connected, it's not actually used. And that's this pin here, it's GP3, so bit 3 of the general purpose I/O port. And the reason it's not used is because it's not very flexible. It can't be used for many different things. So you can see here from the datasheet for the PIC 12F683, that's the microcontroller I used in the charge controller, that GP3 has a very limited range of uses. It can be a general purpose input or master clear reset with a weak pull-up. Now compare that with GP4, you can see immediately that the circuit diagram is much more complex. That can be a general purpose input or output, analog input to the ADC, timer 1 gate input, a crystal or resonator connection, and a clock output. So GP3 is highly limited in what it can be used for. I didn't have a need for a general purpose digital input. This can't be analog either. But so what I did was I set it to master clear, partly because of this weak pull-up. Now there's a section here in the datasheet on a recommended circuit for connection to the master clear pin, which doubles as GP3. And it's got several components. What's that? A 1K pull-up or greater, 100 ohm resistor there, capacitor 0.1, and an optional switch, of course, for actually clearing or resetting the CPU. But this was a lot of components and I didn't really want to put all that there. And given that the master clear actually has a weak pull-up, I figured that would be good enough, and I actually left that pin completely disconnected and floating effectively. No, not floating, because it's got a weak pull-up. So the idea I had was during test, while this thing was sitting on the test bench modulating at nominally 13.5 volts, was to put a switch on this pin temporarily to ground so that you could master clear the CPU. Now that might not sound very useful, just keep resetting the CPU, but the CPU, this microcontroller, has a mechanism inside it for detecting how it was reset. There are a couple of bits here in the status register, TO and PD, which indicate or can indicate how the CPU was reset. So we've got options here for the timeout bit, after power up, clear watchdog or sleep, or a watchdog timeout occurred after power up or by the clear watchdog timer instruction or by execution of the sleep instruction. Now I can't quite remember how it's done, but I did make a video on getting the CPU to determine how it was reset and differentiate between either the master reset pin being taken low or just a general power off and power on. And I'll put a link to that video up here. It's very old, and it doesn't make clear what it's about, but what it was me trying to get the microcontroller to determine how it was reset. So if the microcontroller knows how it was reset, you can get it to branch off and do two different things depending on how that reset occurred. So if the reset occurred because power was removed from the device, which is normal operational use, you could get it to do nothing. If the reset occurred because the master clear line was taken low, which in a sealed unit isn't possible because there's nothing connected to it, then you could get it to cycle through a number of different calibration values to offset the error on the voltage regulator. So my idea was that while this thing was on the test bench with a simulated solar panel on this side and a battery on this side, modulating at nominally 13.5 volts, if there was any error in that voltage, you'd hook up a switch temporarily to this pin, actually it's this pin here, pin 4, press it, and the unit would cycle through. I had in mind 16 different values, 8 which would pull the voltage set point a little bit low, 8 which would pull it a little bit high, and you'd simply keep pressing that switch, and each time you did that it would write the calibration value into E2PROM, and then you'd leave it when the thing had a calibration value which took out the error on the voltage regulator. So the point is, this error in the unit's nominal accuracy can be compensated for. There can be a procedure put into the test setup that can take this error out, and this problem can be completely eliminated. I never got round to doing it while I was manufacturing these things, but it is something I'd like to do now that this unit is going open source for people who want to build this for themselves. Now the E2PROM in this unit is currently used for holding a bit which determines whether or not this thing has the LED enabled or disabled, but because that caused all sorts of problems with people not understanding how it worked, I'm getting rid of that feature. So now I can use the E2PROM inside this unit to hold this calibration value to offset errors in the voltage regulator. So did this calibration problem, this inaccuracy in the voltage set point problem, actually cause me any difficulties when I was selling these? Well, no, it didn't. Nobody actually ever sent one of these things back saying, oh, the voltage set point isn't very accurate. It did worry me sometimes when somebody bought 2 or more units. I would try and send out matched pairs. This one's actually very accurate at 13.49, but if I had a couple at say 13.45 and 13.55, I'd try and send 2 matched ones to anyone who bought 2 units. But no one ever commented on this inaccuracy problem. But it is something I would like to solve, and it is soluble. So I do want to implement this calibration offset capability. Now, interestingly, I found another datasheet for the LP2950. This time it's the LP2950N, and here it says careful design of the LP2950N has minimized all contributions to the error budget. This includes a tight initial tolerance of 0.5% typical, and then extremely good load and line regulation 0.05%. So it seems that this device has half the initial error, or possibly even less than that, of this 0.5%, rather than the, I think it was 1.4% on the other datasheet. Now, although a 1% error in a 5-volt regulator can give you a difference of plus or minus 50 millivolts, because this potential divider here has a 5:1 scaling ratio, it's about 100k total resistance with 20k here across the analog to digital input, then the potential error in battery voltage measurement is 5 times 50 millivolts, so it could be up to 250 millivolts of error, or quarter of a volt. Now these, I never saw more than about 150 millivolts of error, so nominally 13.5. I sometimes saw up to about 13.65 or down to about 13.35, but I never seemed to get much more error than that. So obviously the accuracy of these regulators is in the main quite a bit better than plus or minus 1%. So the fact that I had to sell this product with an error of plus or minus 0.1 of a volt on the set point, and that is quite a lot when it's supposed to be 13.5 and it can be as low as 13.4 or as high as 13.6. It was just annoying. It never actually caused any sales problems. No one ever sent them back saying it's not accurate. But it just annoyed me that this inaccuracy was in there when there is actually a solution. And so I do want to put that into effect and solve this problem once and for all. And so that I can carry on using low-cost voltage regulators, both the through-hole type and also possibly surface mount if I develop a surface mount version of this, I think I want to implement the calibration adjustment facility by pressing a switch during test to offset any error that these low-cost voltage regulators give me. So there it is. I'm now happy to reveal that the PWM5 solar charge controller had an accuracy problem. Some of them went out exactly set to 13.5 volts, but some of them were 13.4 and some of them were 13.6 and all values in between. And that accuracy problem really got to me over the years that I was making them. But there it is. Cheerio.